Hi, I'm Dr. Incognito. In this video, we're going to discuss basic integration. So the integral symbol is this, and when we write the integral of f of x dx, what this is asking for is all antiderivatives of the function f of x with respect to the variable x. So if we write that the integral of f of x dx is equal to capital F of x plus c, then that means that the derivative of capital F of x is little f of x. So integration is also known as anti-differentiation. And capital F is an antiderivative of little f. Capital F is an antiderivative of little f. The derivative of capital F is little f, and so capital F is an antiderivative of little f. The plus c here is called the constant of integration. You see, if the derivative of a constant is 0, and so the derivative of f of x, capital F of x, plus any constant is still little f of x. So when we're looking for the antiderivatives of little f, there are technically infinitely many, because if you have any function here at all, then adding a constant to it is also an antiderivative. As an example, the integral of 2x dx. So this is asking us to anti-differentiate the function 2x. So we have to ask ourselves, what function has derivative 2x? And hopefully that one's familiar, and we can say, okay, that's x squared, because the derivative of x squared is 2x. And this is one possible answer. X squared plus 5 would also be reasonable, as would x squared minus 7, because the derivative doesn't change when we add a constant. So the best answer here, the integral of 2x dx, is x squared plus any constant. X squared plus the constant of integration. So the derivative of x squared is 2x, or another way, the antiderivative of 2x, or I should say an antiderivative of 2x, is x squared. Let's look at a few examples here. What is the integral of cosine x dx? So do we know a function off the top of our heads whose derivative is cosine of x? And hopefully we do. The derivative of sine x is cosine x. So the answer is sine x plus any constant. If you take the derivative of the right side, sine x plus a constant, then you get cosine of x. How about the integral of 1 over 1 plus x squared? Do you recognize that as being the derivative of a particular function? So if you know your derivative formula as well, then you recognize 1 over 1 plus x squared as the derivative of the inverse tangent of x. So the answer here is inverse tangent of x plus any constant. How about the integral of secant squared x? Do you know a function whose derivative is secant squared? That would be the tangent. So the antiderivative of secant squared, or the integral of secant squared x dx, is tangent x plus c. Here is the power rule. The integral of x to the n dx. So do we know a function whose derivative is x to the n? Let's see if we can figure this out. If we start with x to the n plus 1, what happens when we take the derivative? The derivative of x to the n plus 1 would be n plus 1 times x to the n. Using the power rule for derivatives, bring down the power, and subtracting 1 from the power, n plus 1 minus 1 becomes n. So this isn't quite right, because the derivative of this would be n plus 1 times this one. So what we should do here is put 1 over n plus 1, and plus the constant of integration. That way, when we take the derivative of 1 over n plus 1 times x to the n plus 1, we will get 1 over n plus 1, a constant, times what we had here, n plus 1 times x to the n, and 1 over n plus 1 times n over n, times n plus 1 is 1, so we get x to the n. So the derivative of this is x to the n. And this is a major rule here because n can be any real number with one exception. N cannot equal, can you guess what value of n is inappropriate in this formula? Since we have 1 over n plus 1 here, and division by 0 is unacceptable, it's undefined, so 1 over 0 happens when n is negative 1. So the power rule says the antiderivative of x to any power is 1 over n plus 1 times x to the n plus 1. And that's valid as long as n is not equal to negative 1. So before I do some examples of that formula, let's look at the integral of x to the negative 1. Since this formula does not apply in this special case, let's see if we can handle this special case by itself. So rewriting x to the negative 1 as 1 over x, maybe in this form we recognize 1 over x as being the derivative of a particular function. That function would be the natural log of x. But a better answer actually is the natural log of the absolute value of x. It turns out that the natural log of the absolute value of x, whose graph is defined for all x except for 0, and matches the domain of 1 over x, it turns out the derivative of the natural log of the absolute value of x is also 1 over x. So this is the best answer. The antiderivative of 1 over x is the natural log of the absolute value of x plus c. So in conjunction with the power rule, this special example, between the power rule and this special example, we can integrate x to any power. So let's look at a couple of examples there. The integral of 1 over the cube root of x. The integral of 1 over the cube root of x. If we rewrite this as x to a power, that's x to the power minus 1/3. So we use the formula, the power rule, with n equals negative 1/3. We can apply this formula with n equals negative 1/3 because the only value that we cannot use is n equals negative 1. So if n equals negative 1/3, then that means that n plus 1 is negative 1/3 plus 1, which is 2/3. So the n plus 1 that appears here and here is 2/3. So the answer is 1 over 2/3 times x to the power 2/3 plus c. 1 over n plus 1 times x to the n plus 1 plus c. And 1 over a fraction simply means it's reciprocal. So this is 3/2 times x to the 2/3. Another example, let's try integrating a polynomial. The integral of x cubed minus 6x squared plus 4x minus 2. So the rules for integrals are the same as the rules for derivatives. You can integrate term by term, and the integral of a constant times a function is the constant times the integral of the function. So the same process that you would use for differentiating this term by term and leaving the coefficients as part of the answer, those apply in anti-differentiation as well. So using this formula and going term by term, we have x to the fourth over 4 minus 6x to the third over 3 plus 4x to the second over 2 minus 2x, and then plus the constant of integration. The antiderivative of 2 is 2x. That makes sense just intuitively because the derivative of negative 2x here is negative 2. And also we could use this power rule thinking of this as being negative 2x to the 0, x to the 0 being 1. So we can pretend there was an x to the 0 there, and then the antiderivative x to the 0 would be 1 over 1, x to the 1 would be x. And this could be simplified a little bit. 6 over 3 is 2, and 4 over 2 is also 2. So we have x to the fourth over 4 minus 2x cubed plus 2x squared minus 2x plus c. And I'd like to close by looking at a special example. We all know the derivative of e to the x is e to the x. And so the antiderivative of e to the x is also e to the x. Let's make it a little more interesting by saying integral of e to the 2x dx. So what function has derivative e to the 2x? And we can solve this by guessing at first and then modifying our guess. We will guess e to the 2x plus c, and then we will check if you take the derivative of e to the 2x, then using the chain rule, this is e to the 2x times 2. And so this statement is not quite correct because the derivative of the right side is not this, it is 2 times this. So to rectify that, we will take half of this function. If we take half of this function, then now it will work. If we check it, the derivative of 1/2 times e to the 2x is equal to 1/2 times e to the 2x times 2. This times 2 from the chain rule, the derivative of 2x being 2. And here, the 1/2 times 2 cancels. That's the reason we put the 1/2 in the answer, and we get e to the 2x, which is what we wanted. So the integral of e to the 2x dx is 1/2 times e to the 2x plus c. Okay, that was a look at basic integration. Thank you for watching.